Hello, everyone. This is our last lecture involving the simplex method. I'm going to talk about sensitivity analysis, which is looking at, or rather, using duality to understand what happens to the solution to a linear program when you alter the input parameters. By which, in this case, I mean the right-hand side vector of the constraints, so the thing that we usually call b. Although one can extend it also to look at changes in the objective function or the constraint matrix, although that gets kind of linear algebra-y, so we're not going to do that in this class. We're just going to do the easy one. To get started on that, or to give you an idea of where we're coming from, I wanted to point out something first, which is that the the elements in a simplex tableau, you actually can describe them in terms of the input vectors and matrices that you get in a linear algebraic way, which is kind of nice. So mathematically, you can write down where those quantities come from. And so those various quantities are written here. So I'll do the easy one first. You see I've got this in the first bullet there. I've got this tableau. And I claim that the real body of the tableau, the matrix whose rows you're reducing and all that, actually are just obtained by selecting some of the columns of that matrix and extracting them, taking a square matrix that results from them, taking an inverse and multiplying by the constraint matrix. Okay, so that was a mouthful, so I'll tell you more slowly what I mean by that. I'm going to show you here how to reconstruct a simplex tableau if you have MATLAB in front of you and you know what the basic variables are. Okay, so I'm using a shorthand here. You're seeing a script B pop up as a subscript for some of these quantities here. And what that means is, for example, A sub B, okay, this thing right here, A sub B, what that means is it means you take the columns of A that correspond to B, and you build a matrix that consists of only those columns. And in this case, you would take an inverse of that. So why don't I do this first? I'll skip ahead to the next slide, which has an example. Okay, so this is a linear program where you've got A given to you, as well as B and C, and it turns out that the optimal basic set is 1, 5, 3. Okay, so the first, fifth, and third variables are the optimal basic set in your solution. Okay, so then we define this matrix A sub B, which is just taking the first column from A. Okay, you can verify that. 5, minus 1, 2, that's the first column of A. And then the fifth column of A, which is minus 2, 5, 5. And then the third column of A, which is 0, 5, 1. And you can verify all three of those just by looking up. Okay, that's A sub B. It's a square matrix that you just get by extracting those columns that correspond to the basic variables. C sub B is the same thing, only instead of extracting columns, you just extract entries. So C sub B means you take the first, fifth, and third entries out of C. So the first, fifth, and third, 5, 4, and 1, and that's what you see here, 5, 4, 1. Okay, and then you'd go open up MATLAB and you compute the inverse of A sub B, and it's these horrible, ugly numbers here that are, not really important. Okay, so I have A sub B, I have C sub B, and I have A sub B inverse, and I write those numbers down, and I claim that from those values I can recover the simplex tableau as I've written down here. Oh, that pen is not so happy. That's kind of weird. I haven't seen that happen before. Too bad. And you'd recover that tableau by going back here, and let me erase some of these things here. It's there. Because I claim that the value entries of the tableau look like this. So to get that first row, you would take C transpose. So C by definition is a column vector, and so we're looking at the first row, so you have to transpose it, so you get a row vector. You take C transpose minus CB transpose AB inverse A. Okay, I claim that's just what that first row is. It's exactly this, where CB and AB inverse are what I computed below. The upper right corner there is CB transpose AB inverse times B. And then the right-hand side, the values of those variables is AB inverse B. And then the body of that matrix is AB inverse A. And I showed you how to do this in MATLAB down here, if you're interested in doing that. Boy, that pen is annoying. So I've typed in the syntax for how you would do that, and I'm happy to verify that for you right now if you'd like to see it. Yeah, let's do this example really quickly here, just so you can see that is in fact what you get. So okay, I'll do A equals, we'll do this quickly, 5, 5, 0, 2, minus 2, minus 1, minus 2, 5, minus 2, 5, 2, 2, 1, minus 4, 5, B is 10, 5, 6, C is 5, minus 1, 1, 3, 4. My basic variables B is going to be 1, 5, and 3. Okay, and so let's verify these things here. So A sub B, the way you'd write that in MATLAB is you'd write A and then a colon and a comma and then capital B. Okay, and that gives me this thing here. This matrix is exactly A sub B from my slide, which you can see there. And similarly, to take an inverse, you do inverse of A, B, inverse A sub B, and you get this crazy thing here, which turns out to actually be the same values as AB inverse, which you can verify. Just so you know, in MATLAB, if you don't like decimals, if you want to convert something to rationals, you do the command rats for rationals, and you get exactly what you see there. Okay, so now if you had to, for whatever reason, write a MATLAB script for doing a simplex tableau, this gives you a pretty simple way to do it. Right, and we now know if you give me the inputs A, B, and C, as well as the A, B, and C, as well as the, what was I going to say? A, B, and C, as well as the basic variables B, you now know how to build that simplex tableau. I've given the exact commands for you down there. So right down here. Okay, so you've got those now, so you could do that if you wanted to. The reason I'm bringing that up is because we're going to do what's called sensitivity analysis, and that means that these quantities can become important to you. Okay, so the idea there is, again, you got, we'll work in the standard form just because that's how you build tableaus. We'll say we have a standard form linear program, so minimize C transpose X, AX equals B, X not negative, and we have the optimal solution already. So we've solved it, and we say, okay, we've got the optimal solution. The basic variables are, 1, 3, 5, or whatever they are. And so the question of interest for the time being is going to be, what happens if you change some of the values in the right-hand side, that is the vector of lowercase b, right? Like you want to know, okay, what happens? How do I make sure my solution remains feasible? How do I make sure it remains optimal? Things like that. An example of this would be if you're looking at that baker's problem, where you're making two kinds of cakes and you have these limited resources in your kitchen. This is like after you've solved that and you figure out I should make 20 vanilla cakes and 25 chocolate cakes. This is like asking the question, what changes if the amount of flour in my kitchen goes from 30 cups to 35? Of course, you could just resolve the problem. You could just throw it in a simplex method and do it again. But it turns out that using duality, you can actually do some of this stuff a little faster, which turns out to be pretty useful when you're trying to do like millions of different scenarios that you might be simulating in some large-scale system. This is now a way that you can speed that up. And that's called sensitivity analysis. So that whole field is called that. So let's first let's make an observation about the simplex tableau, which is kind of neat. That first row, if you go back over here, the first row, which has those terms that we want to be non-negative, looks like this. Okay, C transpose minus CB transpose AB inverse A. Okay, and here's a thing that is true about that. This expression here is the exact same thing. This expression I've written here, it's the exact same thing, but I've transposed all of it just because I can. It's more, you'll see why in just a second. But anyway, it's the exact same expression, it's just been transposed. So at optimality, you could see that first row has to be non-negative, right? That's how you know that you're done. And so we have, if you substitute that expression that I wrote for the linear algebraic expressions for the simplex tableau, it looks like this. It's C minus A transpose AB inverse transpose CB greater than or equal to 0. Okay, and so here's something to notice about that. What this tells you is the following. If I look at the dual problem, okay, the dual problem for a standard form linear program says A transpose Y is less than or equal to C. If you flip back through the slides, you'll see that appears there. When you take the dual of a standard form linear program, which has AX equal to B, then the dual has A transpose Y less than or equal to C. And here's something that's kind of neat about that. What happens if I take this quantity here? What happens if I take AB inverse transpose CB, and I say, hey, what happens if I plug that into my dual? I say, let's let Y be equal to that thing. Okay, then what do you have? Then you have C, then this condition up here, the optimality condition, which says these terms have to be non-negative. That's the same as saying C minus A transpose Y greater than or equal to 0. In other words, A transpose Y is less than or equal to C. Okay, so that's kind of neat. It tells me that, hey, you know what? It's always feasible for the dual if I take the optimal solution to my primal problem, and I define Y as being this thing here, AB inverse transpose CB. I define Y to be equal to that. That's always going to be feasible for my dual. Okay, and it's always going to be feasible because I have the non-negativity in that first row, because I'm at the optimal solution. So if I'm at an optimal solution, it means the first row is non-negative, which therefore implies that if I define Y as being equal to this particular quantity there, then that's guaranteed to be feasible for my dual problem. Okay, so I've written that in this bolt down here. In other words, the non-negativity condition for optimality is equivalent to dual feasibility of AB inverse transpose CB. Okay, so if you're at the optimal solution, then hey, guess what? Take your basic set B and take AB inverse transpose times the basic elements of C, so C sub B. That's guaranteed to be feasible for your dual. You've got an immediate way to get a feasible solution. In fact, if you do that, if you set Y equal to this thing, it's not only feasible, okay, it's also optimal. And the reason it's optimal is just simple linear algebra. You say, well, what is the objective value if I do that? Okay, what's the objective value at Y if I do that? It's B transpose Y, and we defined Y as being B transpose times AB inverse transpose CB. Okay, so what's that? So let's see, B transpose AB inverse transpose. I'm just bringing the AB inverse and the B inside the parentheses. You get AB inverse B transpose CB, and so what else is true then? AB inverse B actually turns out to be XB transpose. Okay, those are the values of the basic variables, which you can verify if you go back to my definition here of that simplex tableau, and you look at the far right side. Okay, the values of those variables are AB inverse B. Okay, that's the value of those basic variables, and so that means these things here, AB inverse B, that's just XB inverse, XB transpose, and times CB, and then we would say, well, any value of X that is non-basic is going to be 0, and so XB transpose C sub B is equal to C transpose X. Okay, a lot of steps there. Don't worry about that. I just want to drive that point home that once you solve the primal problem and you have that simplex tableau in front of you, you can immediately solve the dual problem. You can immediately get an optimal solution to that dual problem, which is pretty nice. You get that solution. So I showed you already that you can recover that dual solution using complementary slackness. This is an even faster way, right? You just recover if you've got MATLAB in front of you. You just compute AB inverse transpose CB, and then you get that. Okay, so long story short, although it's a little too late for that, if you've solved the primal problem with a simplex tableau, you now have a way of instantly recovering a dual solution. And so that's neat. So we're going to use that observation. We're going to use that observation to try to ask what happens when I change the basic set. Or rather, sorry, you're not going to change the basic set. You're going to change the right-hand side vector here, okay, lowercase b. And let me just see if I remember here. Okay, good. Okay, so let's think about this. Let's start, just to motivate things. I'll start with an example, okay, with some intuition just from the graphical method. So I've got a linear program here, 2 variables, so we can study it graphically. Maximize 4x1 plus 3x2, subject to, and I've got five constraints written down there. Okay, and what I'm going to do is I'm going to say, what happens? I'm going to solve this linear program, but then I'm also going to do the following. I'm going to take this this number 10, and I'm going to change that number 10. I'm going to change it to also 12 and 17. I'm going to say what structurally what happens to this linear program, to the optimal solution as I vary that, right? If the constraint isn't binding, it wouldn't affect me at all, but we wouldn't always want to count on that. So I'm going to say, yeah, what happens to me when I vary that constraint? What happens if I go from 10 to 12 to 17? We'll look at the picture and we'll see. So you might want to pull up the PDF slides here because this might not render so well. But here's the solution to those 3 problems. Okay, here's when you use the right-hand side equal to 10, the solution is here. Okay, and then when I change that from 10 to 12, the optimal solution moves a little bit to the right, but it's still the same corner. And when I say that, what I mean is that it's still the same 2 constraints that define the optimal solution. It's the same 2 constraints, but one of those constraints has moved a little bit. Okay, but the corner is still the same, right? It's moved over as a result of me varying that 10 to 12, but it's still the same 2 constraints that are touching to define this. However, if I increase this right-hand side, then if I go from 10 to 12 now to 17, now that constraint is all the way over here. Oh, what a shame that it did that. That constraint here, I'll drop vertical line. This constraint moves all the way over here. Okay, and now that constraint is no longer binding. The optimal solution is actually this corner. It's 2 other constraints that are touching. And so by varying that right-hand side, by varying it large enough, by making that b large enough, now I've got a new set of constraints that define my optimal corner. Okay, and by an exact analogy, you can say the same thing about looking at the basic set of variables as you vary the right-hand side. It's the exact same. It's a one-to-one correspondence. Okay, so let's look at things in terms of standard form. Okay, so we'll say we've got a standard form linear program. X is the optimal solution. The basic set is capital B. And just to make the notation nice, let's assume that the basic set is just the first m entries. Okay, m is the number of rows that you have. M is the number of constraints. And so we'll say, okay, B is just 1 through m as opposed to something arbitrary, just because it makes notation a little convenient. Okay, so what does that mean? That means X is just a bunch of basic variables and then 0 after that, right? The remaining n minus m values would be 0. And so I have this comment here. If we change the right-hand side vector by a sufficiently small amount, delta B, we know that the basic set will not change. Okay, what I mean by that is the following. Again, you go back to this picture. At first, I took this constraint, which had a right-hand side of 10, and I changed that to 12, which was like a small, I guess we'll say that's a small amount of change. I did that, and the optimal corner was not affected, right? The corner moved, but rather the optimal solution was still the same 2 constraints. It was the same 2 constraints that defined my corner. And if you zoom in on the PDF, you'll see that. But once I made it really big, once I made from 10 to 12 to now 17, and now the optimal constraints actually have changed. They've moved over. It's now 2 other constraints that define that corner. Okay, so the exact same thing is true about the basic set. But anyway, so we'll get to exactly what we mean by sufficiently small in just a moment. That'll be the last part of this lecture. But let's just look at what happens to the optimal solution. Okay, so the optimal solution, which I'm calling x nu, what is it? It's the solution to ABXB is equal to B plus delta B. So we're varying the right-hand side by a small amount, delta B. And you work through the linear algebra, and you get the new solution just being equal to this thing here. Okay, it's the basic entries of x plus AB inverse times delta B. Okay, that's just what that's what that quantity ends up being. So now you can say if you've solved the problem and then someone just perturbs the right-hand side vector b by some small amount, you go from 500 bags of corn to 501 bags of corn or whatever it is. You now have a way of determining what the optimal solution is. You don't have to go back and resolve everything. You just have to do this. You just have to do this one piece. You just compute xb plus ab inverse delta b, which is quite a bit faster. So that's very convenient. You now have a way of doing that. And well, let's ask what happens to the objective function. Okay, how does the objective function value change? So let's ask that. How much does it change by when I vary the right-hand side vector? Okay, so again, the new x is equal to this thing here. And so remember before I said that at the optimal solution, I told you before that you can recover the optimal dual variable y, right? It's y is equal to AB inverse transpose C sub b. All right, so we can compute that. So what's true? So then you know that at the optimal solution, the primal and dual the values have to be equal to each other. So what's true? Let's just plug these values in. So the new objective function, C transpose x nu, is equal to this thing here. So it's the basic values of C times xb plus AB inverse delta b. And then you just carry out the linear algebra. You simplify, and what do you get? You get B transpose y plus Y transpose delta B. Okay, and so what does this tell me? It tells me that if I change the right-hand side vector B by a small amount, delta B, then the objective function changes by Y transpose delta B. Okay, so now all I have to do is look at those dual variables, and you say, hey, what happens if you go from 500 bags of corn to 501? You say, oh, how much is the change? Well, that's 1 bag of corn. So you take the dual variables y transpose, multiply that by the change, and that gives you the amount that you change by. Okay, so let's do an example of this in MATLAB here, CVX, so you can see that I'm not lying. Let's do CVX here, MATLAB. There we are. Okay. Okay, so I'll start. This is going to be the same linear program that I used earlier when I was doing complementary slackness. It's a few slides back. It's in this deck. And I've already cached it here in MATLAB, so you don't have to see me type it out. So I'll write the primal, and I'll do the dual. So the problem looks like this. Minimize 2x1 minus 3x2 plus 6x3. And then subject to, you've got 4 constraints rather, and then some inequality constraints. Okay, so I'll solve that. And the optimal solution is this, 15 and 1 1/7. And the optimal x is 5 minus 2 and negative 1/7. Okay, so we'll just put a pin in that or make a mental note. 15.1429 is the optimal solution there. And okay, I'll solve the dual for you. Now you can, we'll verify that I've done the dual correctly, and we'll see that the objective value is the same. So, this is old hat to all of you at this point, but we had 4 constraints and 3 variables in our primal. So that means our dual has, surprise, surprise, 4 variables and 3 constraints. I'll solve that. And same objective value, 15.1429. Okay, so we're happy with that. We know that we've got the right, so we've written the dual down correctly. That we've gotten the same objective value. So now let's do some sensitivity analysis. I'm going to take, let's do it this way. Okay, so no, I'll do it like this. So let's take my primal problem, and what am I going to do? I'm going to change. What was the one I did before that worked well? I'm going to change the top constraint. Let me go back through. Yeah, I'm going to take my top constraint, and instead of having 4x1 plus 5x2 plus 7x3 equals 9, I'm going to change that to a 10. Okay, and let's see, how does the objective value change? It's 10, and so what happens? The new objective value is 20.4286. Okay, that's the new value. Now let's see if this actually, let's see if this is consistent with the dual problem. Okay, which means the following. I'm going to take, so just to recap, by the way, we started with a problem. The objective value was 15.14. I took the dual of that. The objective value was 15.14 because you were at an optimal solution. And then I changed the right-hand side. I took the 9 in the first constraint and I changed it to a 10. So now let's verify here in MATLAB that I could have done the same thing. I could have figured out that objective value, but without actually solving the problem. Okay, so what do I mean by this? Well, let's take that right-hand side, which was, okay, this is it here in my history on the lower right. So the right-hand side was 9314, and so we'll look at 9 times y1 plus 3 times y2 plus 1 times y3 plus 4 times y4, and that's going to give me 15.14. Okay, that's the dual value. And now we're saying what happens when I change that 9 to a 10, and I get 20.4286, which is exactly the optimal solution to my problem. So again, I solved the problem, and I'm able to predict what the objective value will be when I change these numbers, when I change the right-hand side, by looking at the dual problem. Okay, that's the summary of this so far, which is what I'm able to do. And it's helpful to look at the managerial insights that come from that. Let's look at an interpretation here of this in terms of the dual variables and the constraints. It's pretty interesting. So to summarize so far, I said if I change the right-hand side vector b by, I'll try a highlighter now, maybe that won't have this issue. If I take b and I change it by delta b, the objective value changes by y transpose delta b. Okay, and so here's an interpretation of that, just in terms of words, in a sense, I guess. What does it mean if you look at the ith dual variable, and you look at the amount that you're changing the ith component of b? Okay, if that value is large, then that means that changing the ith entry of b affects the problem a lot. It means it has a large impact on the primal objective value. On the other hand, if that value is small in absolute terms, then it means it doesn't affect you very much. Okay, and so what does that suggest to you? It suggests to you that a big dual variable, okay, a dual variable that is very high, tells you that constraint is really hurting you. Okay, so if you have again, we'll look at the baker's problem. The baker is solving the problem, and finds whatever the solution is, 30 vanilla cakes and 25 chocolate cakes or whatever. And then the baker also solves the dual problem. Okay, and the baker says, oh, you know what? The dual variable associated with the flour constraint, okay, the constraint that I only have 30 bags of flour, that dual variable is huge. Okay, that means that if I change the amount of flour, it has a huge impact on the objective value. Okay, that means that flour is really important to that baker. On the other hand, if you have a dual variable that's 0 for a constraint, that means that having more of that ingredient doesn't help you. Okay, so that if you have an excess of some ingredient, a lot of cauliflower lying around or something, which wouldn't go in a cake, then you say, yeah, that doesn't affect me at all, so the dual variable there is 0. But for eggs or something, there's a very high dual variable, and so that means that is something that affects me quite a bit. So you can do this to analyze a situation in kind of an interesting way. If you have an optimization problem, a linear problem, let's say, and you want to know which constraint is hurting you the most, or which one is affecting you the most, you just look for the constraint with the largest dual variable in sense of magnitude, and you look at that one and say, oh, that one has the biggest value, so that constraint is clearly hurting me. That's the intuition there. That's where dual variables really become useful, as you can use them to determine how the constraints have different impacts on you. Excuse me. Okay, so I made this comment that the change in your right-hand side variable has to be sufficiently small. I said, okay, I gave you that example of the graphical method where when I made that right-hand side go from 10 to 12, it was still the same corner that was optimal, but then 12 to 17 was not. The corner changed. And so that's an interesting question to ask. You say, well, for how long, or how big of a change can I have so that the same set of basic variables is optimal, right? If I really change that right-hand side, then I'm going to get a completely different solution, right? But if I change it a small amount, then it's plausible that you'd have the same basic variables would be optimal. So let's try and express that precisely. This is all just linear algebra at this point, and I think I'll cut through it a bit because it's a little proof heavy, but I'll try to summarize this in a way that at least conveys the idea. So the question again is we want to know how much we can change the right-hand side vector so that the optimal basic set does not change. Okay, and so what do we say? We'd say, well, first of all, the upper row, which is this thing here, C minus A transpose AB inverse transpose CB, the right-hand side vector, lowercase b, doesn't appear there, right? It just isn't there. And so because of that, we'd say, well, okay, if I change b, it doesn't actually affect the upper row of the tableau. And so all we have to do then, it doesn't affect it, and therefore if I change b, you're never going to get that upper row to suddenly be negative. Okay, so it's not it's not that we're worried about that, it's that we were worried about our solution being infeasible. And infeasibility would happen if the new solution, which I derived earlier as being equal to this thing, AB inverse times B plus delta B, that has to remain non-negative. Okay, I claim that if I vary delta B by too much, if I change that right-hand side a lot, this thing might become negative, and then I wouldn't have a feasible solution anymore. But as long as I can maintain feasibility, I'm okay. So we'd like to know how much can I vary that right-hand side while keeping this quantity here, AB inverse times B plus delta B, not negative. So let's just look at, let's focus on varying just a single entry because it's much more tractable to worry about things that way. So we're not going to look at varying, all of the entries at once. We'll just say you pick one value and you vary that. In fact, that's what I did when I had MATLAB open just a moment ago, right? I just took the 9 and do a 10. Okay, so we'll say delta B, and I'll notate that as follows. Delta B is, we're going to call that lambda times EI. Okay, what are these things? So lambda is a scalar, and it's some scalar, and we'll determine what the value of that is in a moment. E sub I, this is an optimization thing. E sub I is a vector that, oh no, wait, this is a linear algebra thing. E sub I is a vector that has all zeros in it, except the ith entry is a 1, right? From linear algebra, it's called the, the standard basis vector, I think. So E sub I is just, it's a vector that has all zeros in it and then a 1 in the ith position. And we're gonna, in this case, we're multiplying by lambda, so then delta B is just a bunch of zeros, but then there's a lambda in the ith position. Okay, so you work out the linear algebra here. You want AB inverse times B plus delta B, which delta B is now equal to lambda EI. That needs to be non-negative. You hack through the linear algebra, what do you get? You get x sub B has to be greater than or equal to minus lambda times U, where U is the ith column of AB inverse. Okay? And so you take AB inverse, which you would need a computer for, and you take the ith column of it, and you call that thing U, and you say, well, as long as x sub B, the optimal solution that I have already, as long as x sub B is greater than or equal to minus lambda times that, then my basic set remains the optimal one. Okay, this is best explained with an example because describing it in these linear algebraic terms is really kind of messy. So we'll do one now. So here's a simple example with two variables. Okay, it's a maximization problem, x1 plus 2x2, subject to constraint that you're in a box, and then the third constraint is x1 plus x2 is less than or equal to 1.5. Okay, simple linear program. We'll look at this one. So you convert it to standard form, introducing 3 slack variables, and you flip the sign of the objective function. So it's minimize minus x1 minus 2x2. And the tableau that you start with would look like this. Okay, you'd use x3, x4, x5 as your starting variables. The tableau looks like this, and when you finish it, it looks like this thing here. Okay, so it looks like that, and so what happens? You have x1 is equal to 1/2, x2 is equal to 1, x3 is equal to 1/2, the objective value is minus 2.5, and so on and so forth. And so you have that written down. And so what is true? So then A sub B, or sorry, the optimal basis, first of all, is x1, x2, x3. And so what is A sub B? A sub B is just the first, second, and third columns of that matrix A. Okay, and A would be the matrix that you would get by inserting slack variables for these terms here, which also happens to be just the matrix that you have here. Okay, so you take A sub B, you take the first, second, and third columns of A, and you get this matrix there. And an AB inverse, if you compute the inverse of this thing in MATLAB, happens to be this thing. Okay, it's this matrix here. It happens to be really nice in this case. There's no fractions or anything. And so we're going to ask the question, what happens if I take that constraint? So the first constraint that I have here said x1 is less than or equal to 1. Okay, once you add in a slack variable, you'd get x1 plus x3 is equal to 1. Okay, which is what I have written down here. x1 plus x3 is equal to 1, slack variable. And we're going to change that. We're going to say instead of a 1, we're going to change that to something else. We're going to make it 1 plus lambda. And we want to know how big can lambda get in terms of absolute value, so how small and how large. What values of lambda will satisfy the situation where the basic set doesn't change? Okay, right now my basic set is 1, 2, 3. I'd like to know if I change that x1 plus x3 equals 1, if I change that 1 to 1.5, is the optimal basic set still 1, 2, 3? If I change it to 2.5, is the basic set still 1, 2, 3? We'd like to know that. And so here's how we determine that based on the argument I had before. I said, what do you do? I said you take the ith column. In this case, we're varying the first constraint. So you take the first column of AB inverse, and you ask under what conditions is it true that x sub b, the basic value entries of x, are greater than or equal to minus lambda times that ith column. Okay, so what is the ith column of AB inverse here? It's the first column, because we're varying the first constraint. So we take the first column, which is 0, 0, 1. And the optimal solution, x sub b, was 1/2, 1, and 1/2. And so we say, what needs to be true about lambda so that this condition holds? Okay, this says 0.5 has to be greater than or equal to minus lambda times u, and u is 0, 0, 1. So what's true about this? Well, you have zeros in these first two entries, right? So they don't. The first two entries are always going to be lambda. So 1/2 will always be greater than 0. 1 will always be greater than 0. That doesn't matter. However, for this last entry here, you need it to be the case that 1/2 is greater than or equal to minus lambda times 1. Okay, multiply that by -1, you get lambda has to be greater than or equal to minus 1/2. Okay, so as long as lambda is greater than minus 1/2, you were then guaranteed that you have the optimal solution, or rather, the basic set does not change. Sorry, so that's how that would work. Oh, I didn't mean to do that. Good. We'll do one more example here, which is a little more enlightening. So again, I had the optimal basic set in my earlier problem was x1, x2, x3. The values of x1, x2, x3 were given here, and the same values of AB and AB inverse. Those don't change. And before I changed, in the previous example, I changed the right-hand side of the first constraint, and now we'll do the third. Okay, and the third constraint, from my original problem, the third constraint said x1 plus x2 is less than or equal to 1.5. Where did my highlighter go? There it is. The first constraint said, oh boy. The third constraint said x1 plus x2 is less than or equal to 1.5. Okay, down there. You add in a slack variable. That third constraint says x1 plus x2 plus x5 is equal to 1.5. Okay, so we're going to vary that now. And we have the third constraint. It says x1 plus x2 plus x5 is equal to 1.5 plus lambda. So we're going to change that, and we want to know how much can we vary lambda by so that this basis doesn't change. Okay, and you do the same thing you did before. This is the third constraint. And so what has to be true? It has to be true that x sub b, okay, the basic values, which are these things here. So this is the basic variables x, 1/2, 1, and 1/2, same thing I had written up there, has to be greater than or equal to minus lambda times u. And what is u? U, again, is we're varying the third constraint. So you look at the third column of AB inverse, and you write that down. So you say, what has to be true about lambda in order for this vector here to be greater than or equal to this vector here? And so what has to be true? So you'd say, well, first of all, there's a 0 in that middle entry. And so this middle entry doesn't contribute to anything. You have 1 is greater than or equal to minus lambda times 0. So 1 is greater than 0, which is always true. But then the first and the third constraints do tell you something. The first one says 0.5 has to be greater than or equal to minus lambda times 1. So 0.5 has to be greater than or equal to minus lambda. Okay, in other words, lambda has to be greater than or equal to minus 0.5. Equivalently, you have in the third entry there, 0.5 is greater than or equal to minus lambda times -1. In other words, lambda has to be less than or equal to 0.5. Okay, so this tells me that if I want to vary that right-hand side from 1.5 to 1.5 plus lambda, then as long as lambda is between plus and minus 1/2, the optimal basic set won't change. So that means I can change that 1.5 from anywhere from 1 to 2, and the optimal basic set will continue to be the same. It'll be 1, 2, and 3. So that's sensitivity analysis, that's duality theory, and from here on out, we're done talking about duality. We're going to get into integer programming next.